Now let's talk about conductors versus insulators. We'll look at semiconductors and superconductors as well. A conductor is any material that allows electrons to flow through it, or to flow freely through it. Remember that when we're talking about charges moving or anything becoming charged, it's generally electrons that we're referring to, as in electrons are what are in a current, and electrons are what are transferred when you charge up some object. Now, why was it that it was electrons? Well, because protons are stuck in this nucleus, right? And the nucleus is, relative to an electron, a very large object that's hard to move. Whereas the electron is this tiny, tiny, tiny thing, very small mass, and so it's easy to pull the electrons off of an atom if they're not tightly bound. And so any electrons in the outer shell of an atom will generally be easy to pull away. So conductors are any materials that have a large number of electrons in that outer shell. And specifically those, they don't hold on to those outer electrons too well. And so the electrons, again, for example, like in copper, the electrons can easily be pulled off of the atom and then propelled through, say, a copper wire. So most metals are conductive, meaning, again, they have these free electrons. But some nonmetals are conductive as well. An insulator is the exact opposite. So any atom or element that holds on to its outer electrons very well, or doesn't have many outer electrons, would represent an insulator. So rubber or glass, right? You can't really run a current through glass because those glass atoms really hold on tightly to their electrons. You might remember we talked about conductors and insulators when we talked about temperature, right, and heat specifically. Conductors transferred heat well, insulators transferred heat not so well. So pretty similar ideas, but it's actually for the exact same reason. So things that are thermally conductive, meaning they transfer heat well, are generally electrically conductive because both are transferred through electrons, right? So electrons moving in itself are moving charges, and these electrons can also take kinetic energy or energy with them, so they can be used to heat up some other object, meaning they're taking heat with it. And for the same reason, insulators are electrical insulators are generally thermal insulators as well. Now, there's another type of material called a semiconductor, and this is somewhere in between a conductor and an insulator. And usually these are useful because they have a transition point. So it could be that at a certain temperature or above a certain temperature, a semiconductor will become very much conductive, whereas below it's more of an insulator. This gives us the ability to create, say, a switch, right? Imagine in a refrigerator, when the refrigerator gets too cold, maybe some sort of material gets to its insulative state and doesn't allow current to run. And when it gets too warm, it'll start to allow current, and we can get the process going to cool down the fridge. There are other ways to get a semiconductor to become either an insulator or a conductor. One possibility is that in its normal pure state, some material is an insulator, but when you dope it, meaning you add some other element or chemical to it, these impurities allow it to become conductive. Other conductors are sensitive to light, so they tend to release charge when light shines on it. Selenium is an example of this. So when you buy a water pipe in a hardware store, the water isn't included. But when you buy copper wire, electrons are already in the wire, of course, right? So when you buy copper wire, it's already made up of copper, and the copper already holds electrons. So when you plug in that wire as part of some circuit, it doesn't need to be filled with electrons, but rather the electrons that are in it are propelled. And as that happens, maybe electrons from somewhere else do move into it, but it does supply electrons on its own. because again, it is the electrons coming from the atoms in that material or whatever conductor we're looking at. That's also why when you turn on the lights, it doesn't take time for the lights to turn on, right? When you flip a switch, the lights turn on immediately, and that's because there's already electrons, say in an incandescent bulb. So there are already electrons in the filament, and as soon as you turn on you flip the switch, these electrons are being pushed through the filament and emitting light. Superconductors are a whole other thing, and they're extremely interesting. And one of the leading fields in physics today, in physics and engineering. They have very unusual properties, a lot of which I could not describe to you, partially because I don't know or I have trouble understanding. But a couple things about them. So one, superconductors are a material that can actually have zero resistance. Resistance is how much something impedes current flow. So if it has zero resistance, it means it's infinitely conductive and allows infinite current to ascend, almost, theoretically. And so generally superconductors do not reach that point until they're very cold. So you may have seen people levitate superconductors, like in this image in the top right corner. When you supercool a superconductor, one way to do that is pour liquid nitrogen over it. It brings it to this superconductive state, and what that does is it pushes all the electric fields around it and allows it to again levitate. This is a complicated process. Again, I can't really explain it. But the fact that a superconductor can have zero resistance is a very big deal. It means that we can have current flow with no heat loss, no energy loss whatsoever. The farther currents need to go to be used, the more energy that's lost or wasted. So yeah. Okay, so let's talk about charging and polarization. We'll actually start with polarization. So polarization is the act of separating charges within some certain object. So it doesn't mean actually charging the object, right? An object is charged when it has more negative than positive, or more positive than negative. Polarized objects can be neutral overall, but their positives and their negatives are separated by some distance. So like in this picture here, we have a negatively charged rod that's brought near some conductive material. You can think of it as even maybe even as water or something, where the negative charges on the rod are pulling the positive part and repelling the negative part of an atom or a molecule, right? You may know that H2O molecules are polarized, meaning that they have a side that's more negative and a side that's more positive than the other. So if I have a neutral metallic sphere, that means that the electrons and protons are all evenly distributed. There's the same number of them, so it's neutral. If I bring a charged rod nearby, it'll say the charged rod is negative, then it'll push all the electrons to the side farthest away from that rod. And what's left behind are the positive charges. Again, we see here that the positive charges aren't moving. So on the other hand, if I had that same neutral sphere and I brought a positive rod to it, is it going to repel the positives away? Well, not so much. Instead, it's going to be pulling the electrons towards it, and thus getting electrons to build up on the side near the rod, leaving behind the positives. So the separation of charge is what gives us a polarization. You can see polarization if you have a balloon. So if you take a balloon and you rub it against your hair, that charges the balloon. So that's not polarization. That itself gives the balloon a negative charge. But now if you take that balloon and you put it next to a wall, if it's charged enough, it can actually polarize the wall and then stick to the wall. Again, being stuck right there to the wall. again, before you do this, take the balloon and just try to put it against the wall. You should see that it doesn't stick. But if you charge it, then it will. And you haven't done anything to the wall. So again, the balloon that's charged, say it's negative, pushes the electrons in the wall, on the surface of the wall, they're out at the outer surface of the wall, away. And that causes the distance between the positives and the negative balloon to be smaller than the distance between the negatives in the wall, which have been pushed away, and the negative balloon. This smaller distance between allows the attractive force between the positives and the negatives to be stronger than the repulsive force between the negatives and the balloon. So again, if you look at this image, right, the negative charges on the balloon are closer to these positive charges, and so this attractive force is stronger than the repulsive force between these negatives and the balloon. Can a process like this cause two objects to repel? No. So as we see here, the negative electron repels the negative charges, and so positives are closest to it. And there's no way for this to occur so that the opposite charge or the like charges are close together and give us a repulsion. So polarization can cause objects to attract. But again, in this example, the wall is not charged. As soon as you move that balloon away, the charges in the wall redistribute to its normal neutral setting. Here's a little animation. So we have here a paperclip, and we zoom in to look at some molecules or atoms in this paperclip. And up here we have some sort of charged rod. As I bring that rod closer to the paperclip, you can see the charges separating. The closer the rod gets to the paperclip, the more it pulls, or more so, the more it pushes the negative charges in the paperclip away, and gives us numerous polarized molecules or atoms. So again, we haven't charged the paperclip here. It's still neutral, assuming it started out neutral, but the charges have been separated. The negatives are pushed away due to this external negatively charged rod. And again, we have a separation of charge. You can cause a single atom to be polarized, right? So if you imagine here, image A, imagine this to be some sort of atom. Take the center to be where the nucleus is, and thus that's where the positive charge is, and then all these blue dots around it are electrons, or at least the electron cloud. You can imagine bringing an external positive charge nearby to this atom. What that'll do is it'll pull the electron cloud closer to it, and the nucleus will remain a bit farther away. So although the atom hasn't changed in charge, if it started out neutral, it'll still be neutral now, but we see that the general electron cloud is a bit off-center from where the nucleus is, thus giving us a separation of charge, or an electrically polarized atom. Here's an image of a water molecule, H2O. And because of its chemical structure, we get these two positive hydrogen atoms that are combined with a more negative oxygen atom. And because of the specific structure of this molecule, there's a separation of these charges that gives this molecule a polarization, or what we call this is an electrical dipole. So an electrical dipole is anything that is essentially polarized. It has a separation of charge, even if it's overall neutral. All right, so let's close up this video because we got about 45 seconds to go, and we'll continue in the next.